Welcome everyone to today's Cyber Physical Systems seminars. This is my honor and pleasure to introduce you today Professor Al-Farouk. Professor Al-Farouk is actually very close by. He's an associate professor at the University of California, Irvine, and he's a director of the Embedded and Cyber Physical System Lab there. He received his Master of Sciences degree and PhD degree in computer science from Europe, Aachen Technical University and Karlsruhe Institute of Technology in Germany. And before joining UCI, he has been also working, researching at Siemens Corporate Research and Technology in Princeton, New Jersey, as a research scientist. His current research is focused on system-level design of embedded and cyber-physical systems, and with particular emphasis on low-power design, security, cyber-physical system security, that is the center of today's talk, and data-driven as well, CPS design. Professor Al-Farouk has numerous publications and 8 US patents and 2 published books as well. And he has received many awards, top best paper awards at the, I would say, the top 3 conference in design automation, both the Design Automation Conference, the DATE conference in Europe, and the International Conference of Computer-Aided Design, as well as many other career awards from both the cyber physical system community and the electronic design automation community. So right now, I'm not seeing the slide. Wanted to make sure I'm seeing Chan Wook's. Oh, no, just, yeah, all right. Wanted to make sure that the slides are ready. And then I leave the stage to Professor Al-Farouk. Please join me and welcome him to this seminar.
Thank you very much, Professor Nuzo, for introducing me. It's an honor to present to the seminar at USC. So as Professor Nuzo mentioned, that I'll be talking about security, mostly about embedded and cyber physical system security. I'll try to explain in a way so that for the students and also for any academic industrial people joining this talk can get the overview of what's happening into this domain, especially today. So I'll try to define in the beginning to give you an outline of the talk. I'll be talking about embedded and cyber physical system security, why it's different, what's new there. And then I'll start talking about cross-layer, what we mean by cross-layer security in embedded systems. Mostly I will be talking about hardware to software. So anything that crosses the layer, the security that it's not only software, it crosses the layer. 2 of the type of security that I'll be talking about, one of them is hardware security, the Trojans. The second one, I'll be talking about side channel attack in hardware software security. And then I'll move my talk to more towards cyber physical systems, where I'll be talking about sensor attacks, basically how the sensors are not vulnerable to. And then I'll be talking about how the actuators are vulnerable too. So you'll get an overview of today about the embedded and cyber physical systems. And most of the work that has been done in my lab. So the examples I'll be bringing what we are doing in the lab. Some of the work I will be also talking about some of my colleagues in the internationally and globally, they're working on these problems. I'll be giving some of their examples too. So what is cyber physical systems, or what is embedded systems? So the cyber physical systems term, I think started from 2006, to be more specific, that NSF started a program, cyber physical systems. And before that, when I was a student myself, we used to call that embedded systems. So what is embedded systems? If you see the definition of embedded systems, I wanted to quote directly from Peter Marvedel, the very classic book that many of the universities are following, that embedded systems are information processing systems embedded into a larger product. That was the embedded systems, mostly low power, hardware software design. Those are the hardware software co-design. These are the things that have been the emphasis of embedded system design. Then in embedded systems, that definitely one of the most important thing, embedded software, which are different than the general purpose software. And I want to quote the definition from Edward Lee, where he mentioned it very clearly that embedded software is software integrated with the physical process. And the technical challenges are a little bit different. It's mostly the managing the time and concurrency, computational system. So concurrency of the computational system. So these are the focus of embedded software. So since 2006, when we came to the cyber physical system, I want to take again a quote from Edward Lee. So to be more specific to cyber physical system, it is cyber physical systems, an integration of computation with physical processes. That's what basically made it different. So below, I try to summarize cyber physical systems is basically embedded systems plus the physical environment along this line. So we get the definition, we understand, try to define before my rest of my talk. I think we need to settle down a definition that we can follow. There are other definitions can come, there can be viewpoints, there is a new terms came, IoT, industrial IoT, there are different terms basically has emerged in the last several years, but I will stick into this definition and try to talk rest of my presentation along that line. So if you have to see the core of cyber physical systems, then definitely understand the information processing is the core of cyber physical systems, and cyber physical systems has different challenges they are focusing today. The challenges like safety is an important problem, verification, design, human in the loop, privacy, security, real-time systems, autonomy, control. So all these challenges had made it multidisciplinary. Honestly speaking, these are the reason that cyber physical systems can never be done by if in a siloed fashion. It needs to be collaborative, it needs to be communicated with other disciplines. And if we can solve these challenges, these challenges are also, in fact, has impact on several applications, not only one application. For example, it is applicable to connected communities, smart and connected communities. It is applicable to manufacturing, agriculture, and energy, automotive, aeronautics. All these applications can get benefited. The core technologies, core scientific discoveries, if we can make in the CPS technology. So these are very important. So I borrowed this slide also from NSF. So these are the things that's happened. So one of the thing that I want to present here that I took the slide from UPenn, that why these cyber physical systems, what are the confluence of trends, what are the reasons that we are moving towards this paradigm, right? So one of the reason is that very classic thing that have happened in the last several decades is the Moore's law, that every 24 months or 18 months, whichever you take, or maybe it has changed recently a little bit because of, we are working in so small, 5 nanometer or even below that technology, that probably we are not doubling the transistors every 2 years, but number of transistors on the same die has doubled and followed this Moore's prediction, basically. So this has been a tremendous growth. And that was one of the driving factor that today we can talk about cyber physical systems. The second trend that over the last several years that we have seen is the integration at scale. By the discovery of internet, we have seen that how much integration can solve problems, larger problems, am I right? Before internet, communication was very, very different, the way we communicated. And today we see that through, I'm talking about this Zoom, I don't need to travel USC, although it's so close to my home because of pandemic, but of different reasons I can talk and communication, I can collaborate. That has been tremendously powerful. So integration at scale. So we are trying to integrate at different scale, and we found through collaboration and cooperation, we can solve larger problems. The third trend that we have seen in the last several years or decades, that human, or in fact, we knew it. It's not that we didn't know, we knew that human evolution is very slow. It takes thousands of years basically to evolve something. But how can we take it to technology development? If you want to talk about that, one of the examples is autonomous vehicle. Most of the cars that we see around, the accidents, or if there is anything happening, the reason behind it mostly the driver's problem, am I right? So, and that has been the driving force, that if we can take the human out of that loop, where there is a critical problem that machines can be more powerful and machine can rather aid. I don't want to go in that situation where we are taking out all the human from regarding automation, but definitely we want to automate this process. And this has been happening for many years. Second industrial revolution, this happened. It has been happening during the third industrial revolution, factory automation. So automation has been definitely a driving force along this line. So I think we understand the importance of cyber physical systems and where we stand today. So now, as I said, the talk today is about security. So before going to my talk, I want to again define some of the terms about security. So in security, there are three letters that are very important. CIA, am I right? So the C means confidentiality, basically that prevent the unauthorized disclosure of sensitive information. So this is one of the terms that needs to be very, very clear. So anything regarding confidentiality we care about. Integrity is another term or another of this triangular, one of the things that we want to make sure that we prevent any unauthorized modification of the system and information to maintain the integrity of the system. The third one is the availability. So we want to make sure that any disruption of service is not happening. So if you know these three terms, confidentiality, integrity, and availability, then you'll be able to follow my rest of the talk easily and be able to classify what I'm talking in this type of security problems and what's happening and how. So you'll see that most of the time today I'll be talking about problems rather than giving a solution. The reason is problems are interesting to understand, and solutions, like students or researchers around the world, will come up with different solutions. Right? So I will mostly present the problems that are exciting at this point in this type of security research. So I try to classify the cross-layer side in this slide. So you'll see what we mean by cross-layer. So in cyber physical systems, if you see the cyber physical systems, if I create a 2x2 matrix, so in the impact layer, I can say that cyber and physical, where is the impact happening? Is it happening in the software? Or if it's happening in the physical side, that means, let's say car will be damaged, there will be an accident, there will be human casualty. So this is physical, really measurable physical thing. So attack can happen also from these two domains. Either it can happen from software side or it can happen from the physical side. Let's say that's touchable, that is a physical entity. So the first place, the cyber to cyber attack. So if the attack has happened from the cyber side and the impact is onto cyber side, so I just want to rather say that I made it in this metric. I try to combine both software and hardware, semiconductor hardware, the electronics part into the cyber. So just to make it clear that electronics is a part of the cyber, and we like to say that this is a part of the cyber system. So in a cyber system, there are also layers. So if you see my graph here, so hardware, OS, software, and user. So these are different layers. We had been already familiar with this thing in computing systems. So when I say cross layer in embedded systems, that means the attack has to start from hardware, and the attack will propagate and go all the way to the software. Or the attack will start from the software or end up in the hardware. So this is the cross-layer security in embedded systems. The second class of security that I'm talking about, that the attack starts from the cyber domain and attack ends into the physical domain. That means if there is anything happen into the hardware or software of the cyber part, and the attack will be manifested basically into the physical domain, like a car. Probably I can hack into the ECUs or control system of the car. The impact will be the car will be stopped. Car can basically be in an accident, or this type of real serious physical impact can happen. Or the third type of thing that I classify is the attack can start from the physical domain. You can try to hack something into the physical domain, do something into the physical domain to do change or steal CIA, anything on the CIA part from the cyber domain. For example, in my lab a couple of years back, we have shown that I can steal the IP, intellectual property, of a 3D printer just by listening to the acoustic sounds or by analyzing the electromagnetic data. So this type of security are cross-layer security that falls into the physical to cyber domain. The other type, the very end type of thing, that if I can change into the physical domain, that goes to the also change into the physical domain, may go through the cyber domain, may not go through the cyber domain. But that's still a security vulnerability. But probably I will not focus on the last quadrant that much. I'll be focusing on to the first three quadrants today in my talk mostly. So what are the examples? Am I right? Lots of examples happen. In fact, last 15 or 20 years, if you go back, start looking into embedded and cyber physical systems attacks that has been in the newspaper, couple of newspaper things I will show today, examples I will show today. Like one of the examples that happened in 2014 in German Steel mill examples, that was a SCADA control system thing. We all know about the Stuxnet attack in Iran in 2010. That was a big news to the centrifuges, basically. Then we also know that one of the early attacks in 2000, in the beginning of this century, it was in Marochi wastewater treatment plant in Australia, where a disgruntled employee basically wanted to spill the wastewater into the field, into the public places and all these things, even the parks. And then we have recently seen that many examples of drones, cars, attacks and security vulnerabilities and that was reported. Most of them are reported into the media. So then I'll start now giving examples of cross-layer attacks. So mostly software and hardware part, the first quadrant part. And I'll start with the Trojan, hardware security, hardware Trojans. So if you see, one of the things that in embedded systems world or in hardware world, we have been, or security world, whichever you follow, one of the fundamental principle or assumption was that hardware is trusted. That means underlying hardware is trusted, and whatever software I'm basically building on top of it, those software might be basically vulnerable. And security people, most of the people in the world for many, many years had been only concentrating onto the software security. But if I just take the trust issue out of the equation, if the hardware is not anymore trusted, then what will happen? That will be basically absolutely different paradigm. And it happened. In fact, we have seen recently many examples like this Intel ARM of any of the basically microarchitectures, basically instruction set architecture that you see today are vulnerable to side channel attacks. There has been many, many examples. People have shown it that all these microprocessors that you see are vulnerable to side channel attacks. Then we have seen recently there was a huge media article about Spectra and meltdown attack. That Spectra meltdown attack basically the completely basically said that the trust, you cannot have any more trust between the software and hardware partitioning. Same thing for meltdown too. And also, other memory rowhammer attack was one of the examples that in memory you have seen that also got a huge attention. So classify wise that now in untrusted hardware, we have basically this hardware security can happen from side channel attack. It can happen from attack security vulnerabilities into the architecture, computer architecture side. For example, the meltdown and Spectra, or the last one is the hardware Trojan type of security vulnerability. So I will not explain meltdown and Spectra today. I'll be mostly focusing on side channel and hardware but there can be a lot of literature that you can read recently, and many of our colleagues are working in many universities on these two type of computer architecture security. So if you focus on the hardware Trojan security, so the question is, can I intentionally basically insert some malicious circuit or malicious hardware? And if I insert, can I break all the CIA impacts that I talked about? I can break the confidentiality, so that I can leak some sensitive information. I can change the functionality. That means I can break the integrity. I can even basically denial of service. I can deny any of the service. And on top of it, I can in fact impact the reliability, like the performance degradation, like the bathtub curve you see here. Rather, typically any semiconductor hardware follow the bathtub curve that their reliability follows like that. But the question is, can I accelerate the aging? Can I accelerate the aging through some hardware Trojan? What is the interest? Who will be doing it? Of course, the competitor can do it. Am I right? If there are two different companies doing similar type of product, one company might be interested basically to harm the other company, and which is not unheard of in business. And we have seen these examples in literature. Although this is an extremely very confidential issue, not many media article comes along this line, but we have seen that how a couple of examples that we have seen recently, that how the Amazon and Apple servers are attacked basically by Chinese provider on the semiconductor hardware, and how those are basically impacted or going to impact these data centers, and how eventually there is a lawsuit and all these things happen. And then we have seen also an example in the beginning of this century that one of the, during the Syrian war, that how one of the radar system that was reported that had used the backdoor, and it was one of the Israeli jets, basically, if you see my screenshot, used the backdoor, and it is it is a rumor. I don't know how true it is, but it was reported in IEEE Spectrum that they use the backdoor, probably they use the backdoor, hardware backdoor to jam the radar system, so and so. So these are real problems. But in lab setup, we have shown several of such attacks. And why this type of security vulnerabilities are happening. So if you see, just look into the semiconductor supply chain, starting from specification to all the way to product distribution, then you will see from, if you follow specification, architectural design, RTL simulations, and physical design, fabrication, testing, packaging, and there are so much of vulnerability into the entire supply chain that anywhere into the supply chain can basically, there is a possibility that some sort of malicious hardware or some sort of malicious description can be inserted. And why it's possible? Because of this distributed nature or distributed supply chain nature of the semiconductor hardware. No single company nowadays, Intel has some capability, but most of the companies you see around have basically needs to have follow are fabless, or you depend on third-party IPs or depend on other supplier, and there is a huge amount of connectivity, or there is a huge amount of dependency in the supply chain. So in this supply chain, there can be basically anywhere in the supply chain, there can be people, there can be malicious attack in principle. And in the last several years, I would say that since this hardware Trojan research became very interested, many people started working on, and we have seen in the I would say more than 12 years, there has been a lot of publication came out. So you'll see that I try to I'll share the slides, in fact, with Professor Nujo later, so you can see and follow this thing, that there has been a tremendous amount of different types of attacks into this thing, and there has really lots of papers, like 48 on type A, and there's been many, fabless SOC design and so has been really people have been trying to work. So this work has been extremely popular into the design automation community and hardware security community, and this got attention, in fact globally in research as a research topic. Many of the people are working. So my lab started working a couple of years ago on hardware Trojan problem, and our basically focus was we had been looking at the way people had been looking, if we want to classify that how people had been looking into this hardware Trojan identification, mostly for detection. The mostly people in post-silicon, after the fab has been done, the type of work people had been doing, one was a functional testing, basically. But imagine that most of the Trojans are not triggered. That means they are hiding somewhere that you cannot really find it during the testing time. So this was a big problem, finding the functional during the functional testing. Then second group of people try to use the side channel analysis. When I mean by side channel analysis, that means people had been trying to use, when you are running the chip or executing the chip, that emits lots of other physical parameters like power, like electromagnetics, or other modalities. And if I can analyze those other modalities, is it possible to identify if there is any anomaly, if there is anything that doesn't add up, basically, to compared to a standard design, we can do it. And then definitely opening up the chip, putting under the microscope, and going one by one transistor and trying to reverse engineer this type of, but which is extremely expensive, extremely time consuming, and didn't get that popularity basically in the world. So what we had been trying, we had been following the side channel analysis. We had been working for a Navy project, ONR project, where we had a different set of goals. Today, the work that I showed you, that for the last 12 plus years, the amount of work has been done, they had a couple of assumptions. Typically, their transistors are big, but now transistors can be just, hardware Trojan can be as small as one transistor. And we had been basically, and hardware triggers, basically, they don't trigger that much, or they are activated very less amount of time. So the question is how we can even understand when they are not basically triggered. Can we identify it? And all the work, previous work, had been relying on a golden chip. That means there is a good, very good chip somewhere hidden, and we need to compare with the golden chip, our any XYZ chip. But the question is, where do I get the golden chip? Who knows the golden chip is trusted? So these are the important parameters we had been, all the existing work has been doing. And then definitely the chip that we are building is under lots of process variation that today we are talking about 7 nanometer, 9 nanometer technologies that has a huge amount of process variation. It has an aging effect, temperature effect. So these are the different problems we are talking. And unknown Trojans. Trojans are not typically known, am I right? It might be easy to find a known Trojan, but the question is, just like software security, there can be unknown Trojans anytime anybody can develop, which we don't have knowledge. The question is, how do we understand those type of Trojans? So you see, if you are interested in this area of research, so these are the research challenges I try to put here. I think this is more exciting for young researchers or those who are already working on this area to address going forward. That's what I wanted to highlight. What are the challenges basically today after 12 years, we are still struggling to basically go forward. So I will not give any solution, as I said, rather I'm giving you the research challenges. I hope that excites you and that encourages you to read more towards that direction and try to identify problems and solutions and work for that. The second problem, again, I'll be talking problems and issues that's happening, the side channel attack. The side channel attack got huge popularity basically when Paul Kosher, basically in 1995, he showed that all these embedded system smart cards that we had been building are vulnerable to basically side channel attacks like through power. And what happened there, basically, mostly the smart cards that are microprocessors, the SoC that we had been using, we had an encryption engine like RSA or DSS. And this, if you can steal the key, eventually you can hack into the system. And knowing the key is a very important intellectual property. So knowing the key was the very big challenge. And it definitely blew the mind. It was really a big thing. And there are a lot of paper later came from Paul Kosher's group showing timing, power, and there are other work along that line. But before that, the question is, side channel is not something new that was suddenly invented. If we go back all the way to Tempest project in NSA in 1972, even basically during the Second World War 1943, we have seen that in different applications to break the Enigma machines or to break basically different encryption systems, different types of side channels had been used, basically either using microphones, inserting a microphone trying to get signals, or inserting some visual technologies. We have been trying to basically use side channel. If we cannot go into that directly into the system, we try to get into the system. But suddenly in the last 2 years, so this is the big area, that cross-layer attack that has been already into literature, very interesting area. In the last 2-3 years, one interesting thing came. That's basically I'm going to present. What is the new thing that people suddenly became excited about? Machine learning, am I right? And I understand that many of you are here also probably working on, are very interested on machine learning. And we have seen that these machine learning models are considered as a very intellectual property about sensitive data. And this hacking this machine learning model or trying to stealing this machine learning model has become a very important research challenge today. So why it's important? Because it's a big market, am I right? Every big company that you can name of today are using machine learning models, starting from computer visions in autonomous vehicle, all the way, any embedded devices, even healthcare application devices today are using machine learning models. And these machine learning models are definitely a very intellectual property, which I will show you in a second. So in the beginning, if you see the paper that came in 2018, basically from one of the groups, and in this group, basically in Hong Kong, they try to steal the basically the training data. And by the way, I'm just presenting the work which are cross-layer. That means there is a hardware-software interface. We are trying to do in the hardware something that to steal something into the software, or the other way around. So you'll see that in 2018, this paper said that how we can steal the training data. That was also important because training data nobody want to share. Maybe a company is very interested, spend a lot of time, money to collect that training data. And the question the group had been trying to do, they had been trying to use different side channels for the computing hardware. That means in the microprocessor, like the timing information or power or electromagnetic data, they try to capture it and demonstrate that using those information, they can steal the training data. Then the challenge started getting momentum in 2019 and late 2018, that can I steal the model? Because now model became a very important thing. Why? If you see the bottom right graph here, from 2013 to 2017, this is one of the graph. If you see the ImageNet basically challenge, like from the AlexNet all the way to RasNet 152, the accuracy has improved from 83.6% to 95.51%. Am I right? So accuracy has increased a lot. And it took almost like a long time, almost like 4 years to go from AlexNet to RasNet. Imagine so many people are working today. Even then it took 4 years. And this is an extremely important IP. So in a company, in a whoever working in this thing, creating a very good model takes time. Like here in this VGG model, if you see the left bottom picture here, and you see that this has already, this VGG model already has 13 convolutional layer. It has 3 fully connected layer and 138 million parameters. Now, this is a customized VGG16 architecture. If I can steal this model, that is a huge benefit of, accurate benefit for the competitor, for many of the people who might be interested on this model directly. So you see the challenges are shifting. And after this moment, basically, as soon as people realized that this has a value, lots of publications started coming. So one of the papers that got in Usenix 2020 was basically using CPU side channel attack. Am I right? They've been using the CPU side channel attack. Then I have recently read another paper using FPGA electromagnetic side channel attack, how to steal the model. Then I recently was looking into another paper that also got published in Design Automation Conference 2020, where people had been using the FPGA power side channel attack. Then more other paper, even in the microcontroller, into the embedded systems domain. Shivam and his group basically published in Usenix 19 this paper, and there are other paper like GPU side channel attack and GPU side channel. So GPU became also very important. So there are a lot of work. So just as a disclaimer, if I haven't referred any paper, that doesn't mean that I wanted to say that this paper is more important than the other paper. Maybe I have missed the paper, or maybe I didn't read the paper. But again, my intention is just to demonstrate that there has been a lot of work into the community, both in security community and into hardware community, design automation community, embedded systems community, along this research line. So as a researcher, this is quite exciting to look into. So my work, my lab started looking into this problem several years ago, and we recently published a paper in DSN. Among many work, I'm presenting this work, where we showed that what we call leaky DNN, and we showed that just by looking into the context switching of the GPUs, that today the amount, all the GPUs that running into the server system, if you look into the server, mostly that anybody shared server, the GPU basically can be shared if you are using a shared server, shared GPU into the cloud or in a data center, anybody can basically run their model into that into the GPU. And in an ideal world, there should be no direct access. Am I right? Because the systems are built in a way that there will be no direct access between these two people, these two green people. If the green people are good, that's fine. But one of these green people might be a red people. Am I right? The bad guy. So what the bad guy can do, if he knows that he's using a shared GPU, he, rather than running any good program or any model, he can just dump a malicious code. Today, there are many GPUs. I will basically invite you to read this paper in details, that you can download the malicious code, and eventually just by observing the GPU context, you can eventually steal the code. And we have shown in our work, the VGG example that I was showing a few minutes back, the VGG16, we were successfully able to basically reconstruct all the layer type, including the sequence, with an accuracy of 95.2%. So almost like out of 16 layers, we are able to get all the 15 layers absolutely correctly. And even the hyperparameters, if you see the hyperparameters like this, all this, C and the hyperparameter, if you see, this was the only misprediction on the pooling layer that we had, the bottom part that I highlighted with red, and couple of basically hyperparameters, like here, there are hyperparameters. So this is exciting. Out of 68, we're basically 57 hyperparameters we're able to predict. accurate with more than 82% accuracy. So that gave us basically extremely knowledge that how these cross-layer attacks are becoming more and more popular, how they are so important to look into. So we started recently looking into FPGA accelerator board, and also looking into similar approaches, that how if FPGAs are getting vulnerable and what we can do, what are the side channels that we can use. So there are a lot of work, because FPGAs are also used into the data center, also into the cloud. They're shared FPGAs, and there are lots of vulnerabilities are happening into the FPGA, shared FPGA architectures, and so on. So hopefully you got excited about the possibility of cross-layer attack in embedded systems. Am I right? So purely, I try to show all the cross-layer. There are definitely other security work. I'm not touching on it. They are very important security attack, but my focus was today to make you clear that what are the cross-layer things that happen. So now, this part, I hope that you got it. Now I'm moving to cyber physical systems, because each of the cyber physical systems depends on the sensor. This has a huge dependency on sensor. And again, sensors are typically in a, if you see that, you will expect that sensors are trustworthy. You have a basically trust on the sensor. But if you top left, if you see the basically the sensor architecture, what happens that in sensor, you have the environment in the yellow highlighted part, and then typically, you try to get the data from the environment, you do the senses, amplify the sensing data, you do sort of filtering, and you do the analog to digital conversion, and you connect it to the microcontroller and so on. So this is the typical architecture of sensor. But some way, if you can spoof these signals, if you can alter the signal before it goes to the sensor architecture, basically computing architecture, then the data it's getting can be basically changed, or it can be basically manipulated. So this has been shown in many several works in recent days. Like this is the work like how $300 projector can fool a Tesla autopilot. So you see that 2020 work. Then we have seen that, sounds bad. Researcher demonstrates a sonic gun threat against a smart device, basically just by using sound, how we can hack into smart devices like any Alexa on those devices. And even, we have seen that how Siri can be used basically to hack. We have seen how drones can be attacked basically using acoustics. So all this modality, acoustics, gyroscope, all these things had been shown tremendously in these days that can be hacked. So you see, there has been a huge amount of growth, and there has been a huge focus today, I can tell you, into the security community, into different top security venues in terms of publications, and people are looking into that, how these sensors can be basically secure. So my group started working along that lines a few years back, basically, and one of the sensors that we started looking into was the Hall sensor that I'll be presenting in a few minutes. So what happened? What we try to do, if you see the attack model, the attacker basically can insert some sort of microcontroller that has an RF module in that, and he can hide in a camouflage container. For example, in a flower vase or a coffee mug. If you do insert those type of small devices, and from far or using internet, basically you can go and create some sort of additional spoofing data you can insert into the sensor that I just presented a few minutes back. So this way you can attack the autonomous vehicle, smart grids, any industrial plants, and even the robotics that my group is working on. So you can basically hack into those systems. So very recently, basically, in fact, just last month, August, we presented this work to Usenik Security 2020, where we demonstrated that the Hall sensor that was like from 1879, the classic Hall sensor that is used for current and voltage measurement in any device, in electronic systems, in electrical systems, and all these systems are vulnerable because Hall sensors are vulnerable. And very recently, we had been funded by NSF to design new types of sensors that are secure sensors. So we started working on that type of sensor heavily, and these are very good. These are the direction that we are looking. And the application that we had been targeting basically of the solar inverter, which are, because the reason was that this is a growing market, like almost like in microgrid, where like in Southern California, if you go, you will see that the penetration of solar, the renewables. So the work is also applicable to wind, by the way. The work that we have done, I'm presenting only for solar today that we have demonstrated, but the same type of inverter can be, the same type of attack can be demonstrated for renewable wind inverter too. So you see that this is a huge market for PV, 14% into the market is penetration. So if you see that, closely look into this, one of the examples basically here, if you will see that this was a 100 kilowatt solar inverter. In fact, it's a large solar inverter. And you'll see, and in your home, probably these are 8 kilowatt, 10 kilowatt solar inverter at home. If you open up this solar inverter, you will see that there are many, many Hall sensors inside in your basically solar inverter. So I will basically show a video now, and I will just change. I don't know whether you can see the video, but hopefully you can enjoy the video. How we attacked it, rather than I go through, I will try to give a live demonstration for that. So this is our setup. We tried to create a microgrid, decoupled it from the main grid, scale it down as much as possible. This is our inverter. We try to shield the inverter so that you also know that shielding does not work, because today most of the inverters are shielded. This is the load, the large load. And then we had been in real time, we had been trying to measure the voltage and the frequency and all these parameters basically. So just a coffee mug. So we are leaving the coffee mug. Anybody can leave the coffee mug or flower vase or anything that basically depending on the platform. You want your remote location, and you can eventually just connect to the system inside. Sounds good. So why it happens, am I right? So this is a classic Hall sensor basically design that is very popular. That's really classic textbook thing that, you know, depending on the, so eventually if I want to basically create a magnetic field here, the equation becomes that V Hall directly is proportional to eventually the B, basically that's the relation that we can see here, the current we can find here. So if we, the magnetic field and all these things, so if we can basically hack into this, add some extra magnetic field, then these sensors can be vulnerable. And this is one of the design, I think the exciting part I have shown that it can be hacked. So this is design of the Hall sensor, this is the controller. And if you take this controller, there are at least, you know, there are multiple Hall sensors there. And if you take just the PV Hall sensor, these two in the left one, which is close to the solar panels, or the other two Hall sensors, which are close to the grid, you can hack any of them. For example, if you basically hack into this PV Hall sensor, the MPPT block you can hack fast, and that will impact the PI controller. Eventually, by carefully knowing the value and carefully basically changing the value, you can go into the PWM inverter and eventually change the parameter. You can do the same thing for the Hall current sensor through the ABC to DQ control block, and also the PLL block basically for the other voltage sensor. So all these sensors eventually can be hacked. And if you see carefully this voltage parameter that I'm showing here, you can eventually, you can make it out of phase and change the completely, you can distort the wave and frequency. And it costs less than $50. We have demonstrated that even less than $50, you're spending less than $50 you can really cause serious problem into the grid. And one of the example, let's say here, then later we simulated a large grid. This was IEEE 13 bus. And here in this, we use this 100 kilowatt generator or inverter. And I showed you one of the inverter before, the real example of 100 kilowatt example, the real hardware. If you simulate this thing, because it's not possible to really run this thing, you will see here that in 2 second time, at 2 second, I basically start the attack. And in less than 8 seconds, I can reduce the 8 second, I can reduce basically the rated value almost like more than 15%. Am I right? And this in 8 seconds, eventually that means that if I can reduce it below this rated value, I can in fact shut down the entire grid. That means it's a blackout. So we have demonstrated that using our attack, you can even cause a blackout. So it's just not a minor change into the frequency or voltage. You can indeed create a blackout. So please read the paper. I wanted to rather demonstrate the problems, solutions people had been trying to do. Shielding will come up with different alloy materials, but we have demonstrated that all these things are extremely expensive or can be hacked, or it's not general purpose. And that's why I mentioned that we're currently working on a NSF project along that line to censor it. So last part of my talk is about actuator attack. I think I'm spending more time. I already spent too much time on the other topics. So let me see that in the next 10 minutes, if I can go over the actuator attack. So what is a P2C attack? So one of the examples that in 2015 we did, that this is a 3D printer. It's a printing 3D printer. It's printing something, a key in this example. And we had been collecting the sound, acoustic sound from the 3D printer. And now, in fact, we can do vibration, electromagnetic, and other modalities. We have done a lot. But still, I'm using the 2015 video. And you can collect the acoustics. And using these acoustics, later you can reconstruct using computer algorithms, either using machine learning or different algorithms. Basically, you can recreate the entire IP. So this type of things was a demonstration that even your actuators are not secure enough, and it can eventually leak information. And using the classic side channel attack that has been applied into microprocessor and semiconductor hardware, we can apply similar attack to the actuators and can steal such information. So you can ask that why such things are important, am I right? Definitely why it gained so much popularity. It was in fact published in 67 newspapers in different languages all over the world. There is a reason for that. In additive manufacturing, especially the application that we had been working on, it is a very important application, and people are using really real world 3D printing has been deployed into real product design, product development today in manufacturing. And the entire industry is already $21 billion. So there was in fact, when we published the paper, Gartner published an article saying that this IP market of 3D printer is almost like $100 billion, and which is an extremely motivating towards going to this type of any type of act. And to understand, give you a perspective, what is an IP in this type of physical systems? Am I right? This is one of the things, a thinking man from Michelangelo, Nefertiti from Egypt, or a Rolls-Royce engine. If you can take, these are the IP for many of the systems industry. But today, because we are 3D printing, the 3D printing is basically becoming like a recipe that is published, written recipe, like geometric shape, process information, machine information. This became the IP for additive manufacturing. So now if I can store this intellectual property into the cyber domain, and if I can steal this recipe, step-by-step recipe, imagine you're cooking something that you don't want to share with anybody, but just by understanding your side channel, if somebody can get your recipe, that means your IP, your very IP is violated, or your secret of your cooking is violated, right? So that's exactly the motivation towards that. And we have demonstrated that how by understanding the G code, it's called in G code in that the manufacturing domain, that explains the travel feed rate, the movement axis, extrusion amount, and so and so, how we can eventually steal the 3D printing information and so and so. So this was extremely motivating for hacking into additive manufacturing. And in fact, this was the first paper on this type of attack in 2015. And after that, there are at least 100 or 200 papers. I don't count these days. All over the world, people are working. I know that many of my colleagues globally started working on manufacturing security, especially this type of attacks and their defense and techniques. So this was an extremely important work that we started looking into cyber physical systems, and especially into the actuator. And we took this work even to the biological systems. Just quickly to give you another example, and we took this to the DNA synthesis machine. So in DNA synthesis, this is a paper that we published in NDSS 20, I believe 2018, 19. It was published in one of the top security conferences, where we demonstrated that, again, using sound, acoustics, you can hack into a DNA synthesis machine. So again, the question is, it's a multidisciplinary work. I had been talking to lots of biologists. I've been talking to people who really, everyday world, they do work with the DNA. And in a DNA, if you go back to your biology class, it's all about ATCG, the helix structure, the classic helix structure. And people try to synthesize DNA today in a synthetic way, because there is an application. There is a huge market for drug discovery, for medical treatment, or in the agriculture domain from crop optimization. In fact, later we found that crop optimization, in fact, there was a lawsuit in Midwest in 2017 that some of the international people, I don't want to name the country, you can look into the news articles basically in my webpage, that those country people, they were trying to steal one of the genetically modified seed in the from US, one of the US basically industry, and that was really in the newspaper, and there is a lawsuit going on today. And the idea is that this structure is very valuable, this ATCG, and if I can steal this thing, this is a very important synthetic data, and it is an intellectual property, whether we can steal this structure and whether this is possible, basically. So we started looking into this thing. We spent a lot of time basically talking to the machine users and trying to understand how this machine works. So this is one of the machines that we have used in our lab. In fact, if you can hear the sound, you clearly see, if you are listening, that there are, you can distinguish different stages and the delivery of base A, base C, and base G. And by understanding those bases, eventually you can probably reverse engineer that what's happening inside the machine. So this was the beginning of our work, and we used one of the, this is only one machine we have at UCI. In fact, we talked with many other universities, neighboring universities, who do not have this machine. So we are lucky to get this machine, and we try to hack into this machine. It was AB3400, which is basically has a market penetration more than 90%. So this is the mostly used machines that today used in labs. And we used an audio recorder. We recorded the sound, and eventually we show that with a more than 88% accuracy, we can in fact classify and we can understand different layers. And then we try to understand that if I use noise, because typically labs are noisy, there are AC sound can come from AC, sound can come from different, the people are working, people are talking. So what are the implications of noise? We try to basically extrapolate the noise and try to understand this data from a noise point of view. We try to understand from a distance point of view that how far my phone needs to be put, because the same work can be done using your iPhone or other phone. This type of analysis we have done in this work. And then we have also played basically rat and cat way, that one of our colleagues in the biological domain, he was trying to synthesize something, and we try to predict whether we can synthesize this. And we found that we can do quite good. We had also some wrong positioning, but it was quite close. Then the point that I'm trying to make here, you'll see that there are lots of rates still, am I right? Accuracy is still not the exact accuracy. Then we started talking with the people in the biology, and we found that domain people already use a tool called BLAST. And in the BLAST, what happened, globally, everybody basically upload the sequence, upload their sequence in either in lab or different fashion they try to upload it. And then we found that if we try to match along that line, and with those limitations, we developed algorithms. In fact, we developed many matching algorithms for doing that. It's the details is in the paper. We can, in fact, find what type of DNA we are predicting. Like if it's an insulin, we can go very close with an accuracy, with a 100% accuracy, we can predict that this is an insulin. And so now imagine a pharmaceutical company spending millions of dollars to produce some medicine along that line, and somebody probably can just steal from a phone, data collected from a phone, and can eventually do this type of thing. So this is extremely valuable, that if we can hack into the actuators and so on. So with that, in fact, I will finish my talk today. I hope that I was able to give you lots of problems rather than solutions, lots of example problems to excite you, to work along that line and motivate that cross-layer security threats are real. And it is becoming more and more important to look into. And definitely hardware is not trusted anymore. You can't rely on hardware anymore. And you cannot also rely on physical environment, that the sensor data, that the data you are connecting from sensor. The environment can be basically also perturbed, and misinformation can be inserted into your sensor. So there needs to be protection in the hardware software side to do that thing. And I try to motivate that the cross-layer attack is not only P2C that goes from physical to cyber. It can be a chain, like physical to cyber. It can go through many layers of cyber and eventually attack into physical, or even go to end up in cyber. So the future is really to be exciting from a research point of view. From a practical point of view, definitely the future is something to be seriously taken care of. And these are important issues that needs to be considered when you are, as a designer, we are designing. So security should be considered as definitely as a first-class citizen, not anymore afterthought. We need to start designing sensors, keeping in mind that security is an issue. We need to design hardware-software interface, keeping in mind that security is an issue. We need to design actuators, keeping in mind that security is an issue. So you see, whenever you are basically trying to build systems as a cross-layer, you need to understand this inter-layer perspective very clearly. So also I demonstrated that the additive manufacturing work, or the DNA work that I have done, or the sensor attack I have done, none of this work can be accomplished just by the knowledge of computer science or computer engineering. You need to have a domain knowledge. And as an engineer, computer engineer, by training myself, I cannot have every knowledge. So it is becoming multidisciplinary. That means you need to work with people, other domain people, where you can communicate. You need to learn each other's language, and you can identify this type of vulnerabilities. And this will become very exciting. And this is becoming, going forward, the research directions are, I see very promising research direction along that line. And definitely defenses must consider cross-layer techniques. And I didn't talk much about defenses today. With that, I want to conclude my talk. I want to thank all the sponsoring agents that has been sponsoring my research for the last 9+ years, and all my students, basically, who are doing amazing work in my lab. So if you are interested, some of you are interested to continue your PhD, if you are listening, if you're a student, or if you're listening from outside, please contact me. We are definitely hiring PhD students and postdoc regularly to work in this area. Thank you very much. If you have any question, I'll be happy to take questions.
Thank you very much, Mohammed. It was a very inspiring and alerting at the same time talk. Hopefully, the companies that are working on RNA right now for our vaccine and so on, they will not be subject to on synthesizing the RNA like Moderna and so on to this kind of attacks, and they can proceed smoothly. So I'll leave the space for questions now. Please feel free to use the question and answer or the chat, or also raise your hand, and we can unmute if you're not able to unmute, and ask directly the questions as well. So I have already actually 2 on the Q&A from our students. So I'll go ahead and start with those ones. So one is about actually superconducting circuits. So I think you were showing us Trojans on CMOS. So, okay, so it is now known that also superconducting circuits might have vulnerabilities, third-party putting undetectable parts in the chip during fabrication or reverse engineering. Yeah, one of our students is wondering whether you have been thinking about these vulnerabilities, also to other kind of technologies then, and whether your lab is involved in this research.
Okay,
or
very good
other
question. Yeah.
forms.
So to answer this question, my lab is working on CMOS. But definitely, all these different technologies that people are working on has similar type of problems. But at this point, my work is concentrating on CMOS to answer the question.
Yeah, thank you. And another of our student is asking about still the hardware Trojans, and the golden chip that he used to produce a reference for the system performance. So is it a viable option to have two different manufacturers such that we increase the chance to detect the hardware Trojan embedded by one company? Or can we perform a physical inspection only one of the samples to ensure that it's not an hardware Trojan, and does use it to produce a reference system performance to test the rest of the examples?
No, absolutely. This is a very good question. In fact, this is the current practice. So, if you see the manufacturing, split manufacturing, people are basically splitting the manufacturing even on one design, splitting the manufacturing different part today. And people are expecting that, by splitting the manufacturing, it will be, we will be able to solve the hardware Trojan in that pipeline. If you're thinking that the hardware Trojan will be inserted in the stage of fabrication in the fab lab, you can solve it probably. Then also your assumptions might be right, I don't know. Then the question is, two is two enough or we need more? So there is always a problem. So I think rather than relying on those luck, chance game, or relying on this type of thing, I think it's better to come up with a strategy. Is it possible to come up with algorithms, methodology, tools that we can take that assumptions out? I think, this is a hard problem. I understand it's a very hard problem, extremely hard problem. If both for pre-silicon and post-silicon, it's not only post-silicon, it's basically pre-silicon problem too, because in the different RTL level, gate level, can we do that without a golden chip? That's why I'm telling, that's a hard problem. Do we have any solution? I don't believe we have a good solution today. We don't have. In fact, my lab is working. Do I want to say our solution is the perfect one? No, our solution still has problem that probably we don't write in the paper, but I can say, yes, we have problems. But these are really hard problems. And I want to encourage people, students, because I know this, most of you are maybe attending our students, to really look into this thing and take it to the next level. And I know that's very exciting time.
Yeah, especially right now, that indeed the design of deep subscale technology is actually often outsourced. And
absolutely. And global, you probably listen to this global politics. So many things are happening that in the next 10 years, I think the entire semiconductor industry, the entire supply chain needs to rethink about this thing. There will be a lot of work along this line. Already has been done some more, but I think too many questions, unsolved questions.
Yeah. So I'll just ask the audience if they have any further questions. You're welcome to use the chat and the Q&A. Otherwise, I will ask just a quick one, just out of curiosity about the leaky neural network and the model. So I was wondering, what kind of threat model were you assuming there to be able to, reconstruct with such high accuracy all the hyperparameters only, and whether you have thought about any defense there or any countermeasure?
Countermeasures, basically, we talked about some of the countermeasures from the hardware vendors, basically they can put, or the system building people that basically check before downloading it into the server or shared resources. But, I don't want to name any vendor here, but, most of these things are still, they try to patch. Before we published the paper, there was a patch, and then we used that patch, and then again demonstrated that this is still, I can download, in fact, in Amazon cloud or any cloud, I can download a malicious code and can get the side channel, and I can monitor what the other people are doing.
Yeah, so this is indeed the field in which attacks and defenses alternate continuously, iteratively.
Absolutely.
Every single few weeks.
And I think there is a reason for that, Nujo. I think one of the reasons is that most of the people are working on siloed and looking, and that's on another message that I want to give. that they're not working on the cross layer. So the sensor work that I have demonstrated today, we're working on sensor and we are playing ourselves, rat and cat, and any solution that you come up with software, you can hack it from the hardware. If you come up with a hardware solution, it's purely not feasible. So there is a huge demand now, a hardware software co-design or this cross layer, understanding the cross layer to solve any problem.
Yeah, and in fact, that's exactly those layers that have been created sometimes to make the design smoother and more verifiable and so on. Then they are usually attacked and could be a vulnerability for them.
You are right that we have made those layering for making design easy, verification easy, validation easy, but now those are somehow making problems.
Right, hence the need to rethink.
Absolutely.
All right. Thank you very much for the perspective and letting us reflect about these issues that are fundamental and may touch your life every single moment. And so if there are no other questions from the audience, then join me and thank again Professor Al-Farouk. We hope to see him in person as soon as possible, also here at USC, one of the first opportunities that we'll have as soon as we'll get back to a more normal setup also for this webinar and seminar. Absolutely. Thank you very much for being with us.
Thank you very much.
Yeah.
Take care.
Bye.
Bye-bye.